My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our international physics webinar. So hope you are well and safe from corona pandemic. And I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program including online international physics webinar. And we have successfully completed our 227 international physics webinar, including 4 Nobel laureate speakers. And today it's our 228th International Physics Webinar. Today we would like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, Vanderbilt University, USA. And we have with us here today Dr. Robert Scherrer, a professor, Department of Physics and Astronomy, Vanderbilt University, USA. And he has already connected with us. So I'd like to welcome our speaker. So good morning, sir, and good evening here.
Good
So
morning.
thanks for accepting our invitation, sir. And
Okay.
it's our honor and privilege to host you in our international physics webinar. So before going to you, I'd like to introduce you with our students and viewers.
Yes.
So yeah, thank you. So dear student and viewers, I think you have already come to know the title of the students' international physics webinar. Title is "What is the universe made of?" Very exciting and interesting topic. I think you will enjoy it. And our speaker is Dr. Robert Schorer, Professor, Department of Physics and Astronomy, Vanderbilt University, USA. And Professor Robert is a professor and Department of Physics Astronomy. Uh, he was a chair at the department, but recently he's currently working as a professor. His research area is cosmology, encompassing work on dark energy, dark matter, Big Bang nucleosynthesis, and the large-scale structure of the universe. He is also the author of the quantum mechanics textbooks and has published several popular science articles and science fiction short stories. And he maintains a blog on science and science fiction. We can see his educational background. He has completed his bachelor degree in physics from Princeton University and master's degree in physics from Cambridge University, and he completed his PhD degree from University of Chicago, and his thesis supervisor Professor Michael S. Turner. And we can see his professional experience. So he has started his professional experience as a postdoctoral research associate in 1986 at Harvard University, and then he joined as a postdoctoral fellow at Queen Mary College, University of London in 1987, and he stayed there up to October 1987, and then he joined as a assistant professor at the Department of Physics, Ohio State University, January 1989, and in 1993 he joined as assistant professor Department of Physics, Ohio State, and in 1997 he joined as a visiting scientist, theoretical astrophysics group Fermilab, and in 1998 he joined as a professor of the Department of Physics and Astronomy at Ohio State University. And from 1999 to 2003, he was a vice chair for undergraduate studies at the Department of Physics, the Ohio State University. Uh, from 2003 to now, he has been working as a professor of the Department of Physics and Astronomy at the Vanderbilt University. And this is honor and awards. He got Marshall Scholarship, McCormick Graduate Fellowship, and NATO Postdoctoral Fellowship, the Ohio State University Alumni Awards for Distinguished Teaching, Fellow of the American Physical Society, Fifth Prize Gravity Research Foundation Essay Competition, Klosteg Memorial Awards, American Association of Physics Teachers, and this is the research interest. He's working in different interesting fields like Big Bang nucleosynthesis, large scale structure, cosmic microbe background, dark matter and particle physics in early universe, and dark energy. And he has wrote 2 books, and the first one, the quantum mechanics, an accessible introduction. Another is instructor solution manual of quantum mechanics. This is the referred publication, just 10, many of them. So thanks for all of your patience. Now it's time to go to our speaker. Sir, it's your time, sir. You can start your
Okay.
session.
Thank you.
Yeah.
All right. I'll bring up my screen if there's any issue. Let me see if
Yeah,
there's any.
I'll inform you. If,
Yes, just interrupt me. Okay. So what I want to talk about, can you hear me okay?
yes, everything is
Okay.
okay.
What I want to talk about today is what is the universe made of? And of course, we know now that our original idea that the universe was made of just protons and neutrons and electrons is almost certainly false. And we've kind of entered a golden age in cosmology. And I would say over the past decade or maybe over the past 20 years, we've developed a very clear idea of what the universe is made of. And the odd thing is that it's weirder than we could possibly have imagined until about the year 2000 or 1990. We really believed that the matter we saw around us was really all that there was. But we've come to understand that the universe is made up of some exotic components. And what I want to do today is talk a bit about what those components are, and even more importantly, why we think that they are the dominant components in the universe. So if I draw a little pie chart here, this represents what we think the universe is made of. So this little wedge is the stuff we're made of. So these are atoms, molecules, essentially what's sometimes called baryonic matter because it's made of neutrons and protons. That's what gives us most of our mass. And you can see that we think it makes up only a very tiny fraction of the matter in the universe, maybe 5%. A much larger fraction of the energy in the universe, about 25%, is made up of what's called dark matter. And then about 70% is what is called dark energy. And what I want to do is try to give you some understanding of why we believe that these components exist and that they are the dominant components in the universe. Because if you're going to make extraordinary claims, you need very strong evidence. And we think that the evidence is, in fact, very strongly in favor of this. But I want to talk about that today, and then we'll talk about how we might go looking for these components. So why would anyone believe this? Well, let me give you a little bit of a historical introduction to cosmology, because it's something people often don't appreciate, how far back this field goes and how we came to believe these things. The person who really is the founder of modern cosmology, I would say, is this person who you've probably never heard of. His name is Vesto Slipher. And he was working in the United States in Arizona with the telescope there back in the between 1910 and 1920, around the time of World War I. And what he was doing was looking at distant galaxies and measuring their velocities. Now, when we look at galaxies now through modern telescopes, we get these beautiful pictures, which are in full, mostly artificial colors. And you can see that it's obvious that these are collections of stars just like our own galaxy. But back when Slipher was working, that wasn't completely obvious. And in fact, these were sometimes called nebula, nebulae, which just means clouds. Because in the telescope of the day, the telescopes of the day, you couldn't resolve them into these pretty pictures. All you saw were these kind of blurred objects. And there was a debate as to whether they were other galaxies like our own, or if they were just gas clouds. Now, how was he measuring the velocity? Well, of course, he was using the Doppler effect. So as you know, when a light wave is moving toward you, it gets compressed and the wavelength goes down. When the wave is moving away from you, the wave gets stretched and the wave goes up. And so it's actually a fairly easy measurement to make, to look at distant objects where you know what the frequencies of the spectral lines ought to be. You compare it to what you see and you can get the velocity. Now, I'm a theorist, so I'm going to tell you that observations are easy without ever having made them myself. In fact, I probably would be completely incapable of making these measurements. But as astronomical measurements go, this is an easier measurement than most. Now, Slipher was expecting that these galaxies would be moving in kind of random directions. Some would be moving toward us, some would be moving away from us, and he could measure the average motion of the Earth relative to these galaxies. But when he actually made his measurements, he made a rather astonishing discovery. What he found is that almost all of the galaxies were moving away from us. He measured, I think, 41 galaxies, And out of those 41, 36 were moving away and only 5 were moving toward us. And the ones that were moving away from us were the ones moving with the highest velocities. They were actually moving the fastest. This was not something he expected to see at all. And what he had discovered without realizing it was the expansion of the universe. Now, you've probably never heard of him. He's a rather unhappy looking gentleman here. That's just how they took photographs back then. But one of the reasons for this undoubtedly is that the person who gets all the credit for this is this man instead, who you almost certainly have heard of. His name is Edwin Hubble. Now, the reason that Hubble gets the credit for it is that he did a more important measurement. What he measured was not just, sorry, let me go back a minute. He measured not just how fast these galaxies were moving, but he made the more difficult measurement of measuring how far away they are. And that is a much more difficult measurement to make in cosmology. It's still a difficult measurement because the way that we measured the distance to faraway objects in astronomy is to look at their apparent magnitude, how bright they look, and compare it to their actual brightness if they were right next to us, and then use that to calculate how far away they are. So a very bright object that appears dim has to be very far away. A very dim object could be close to us and appear very bright simply because it's close. The problem with that statement is that there are very few objects whose brightness we can determine absolutely. That is, how do we know how bright an object actually is? And this is a search in cosmology for something called a standard candle. A standard candle is something whose brightness we know intrinsically. And Hubble used famously a type of variable star called a Cepheid variable. These are stars that pulsate. And what he was able to show is that for stars inside, nearby, where you can measure the distance through other means, what he was able to show is that the intrinsic brightness of the variable star is related to how fast it pulsates. So Cepheid variables that pulsate rapidly are intrinsically dimmer, and Cepheid variables that pulsate more slowly are intrinsically brighter. And armed with this information, he was able to find Cepheid variables in distant galaxies and figure out how bright they actually were, compare them to how bright they appeared to be. And so he could repeat Slipher's measurement, but now he could compare the distance to distant galaxies to their intrinsic brightness. And what he found was a linear relationship between the distance to the galaxies and how bright they actually were. And this is very important. This is the Hubble relation. It's so important it's named after Hubble. And what he showed was that the speed of the distant galaxies is actually proportional to their distance. That is, a galaxy that is twice as far away is moving twice as fast. A galaxy that's 3 times as far away is moving 3 times as fast. And the reason this is important is that this is the only expansion law that is possible if the universe itself is expanding. And I've drawn an equation down here, but rather than look at the equation, I think it's a little bit easier if you look at this diagram. The point is that in an expanding universe, every point appears to be the center of the expansion. And so if you look at these points as they expand, in order to maintain this expansion law, here's the points today, and here's what it'll look like 20 billion years from now. You can see that in order to maintain this expansion law, the more distant points have to be moving faster. The speed at which they move is proportional to the inverse of this slope. So this point has to move very fast to get further away and maintain this proportionality. The one close to me doesn't have to move quite as fast. And if you do the math, you'll see that not only do the more distant galaxies move away faster, but they move away in a proportion to their distance. That is, their speed, in order to maintain this separation, has to be proportional to their distance away from me. So Hubble discovered what is now called Hubble's law. That is, the velocity of a distant galaxy is proportional to its distance. And immediately after this, various people, Friedman and Lemaitre, equation for the expansion of the universe. And what they showed was that there were two possible fates for the universe. The universe could expand forever. And this is my pathetic PowerPoint illustration. Here's that you throw an apple into the air and it goes away forever, or the universe could recollapse. And this calculation actually is not a difficult calculation because it's one that you do in freshman physics in college or in high school. It's simply a question of whether something has an escape velocity or not. If I throw an object away out from the Earth's atmosphere, if its velocity is such that its kinetic energy is greater than its potential energy, it'll go away and escape to infinity. If I throw an object on the Earth's surface and the kinetic energy is lower than the potential energy, it will simply fall back down again. Now, the difference between this calculation and one for the universe is that we know the mass of the Earth, and we know the potential energy, gravitational energy from the surface of the Earth. And what we can control is the velocity. We can control how fast we throw an object into the sky, and that determines whether it's going to go up forever or recollapse. With the universe, it's the opposite. We know the kinetic energy of distant objects because we can measure their velocities. We can use the Doppler effect and measure their velocities. So we know the kinetic energy of distant galaxies, but what we don't know is the gravitational potential energy of the universe as a whole, because that depends on how much matter there is in the universe, and that depends on the density in the universe. So a high density universe has more gravitational potential energy than kinetic energy, and it recollapses. A low density universe has more kinetic energy than gravitational potential energy. It expands forever. And so this launched cosmologists on a multi-decade search to determine how much matter there is in the universe. And there's my movie playing again. The first question is, how much ordinary matter is there in the universe? Now, you might think what we could do is just look at all the stars in the universe and all the shining gas and add that up, and that would tell us how much matter there is, how much ordinary matter. But in fact, that's not a perfect calculation, because there's matter in the universe which is dark, which is not shining. And I don't mean the dark matter that's, exotic dark matter. Even some ordinary matter doesn't give off radiation. So cold gas or cold dust, it doesn't radiate. It just sits there and is hidden from us. So the best way, ironically, to find out how much matter is in the universe is to look at the early universe. Because in the first few minutes of the universe, fusion reactions take place that produce some of the elements that we see. Now, most elements in the universe, the heavy elements, the stuff we're made out of, like carbon and oxygen and nitrogen, are made in stars and in supernovae. But a small fraction of the elements were actually produced in the first few minutes of the Big Bang, mostly helium. So most of the helium in the universe, which makes up about 25% of the universe, 25% of the ordinary matter, was made in the Big Bang. And there also are some other elements that are made in trace amounts, like deuterium, which are produced in very small quantities, but they're very difficult to make in stars. So if we see deuterium in the universe, we know that it was most likely made in the early universe. And you could do calculations of this, and I've done them. And in fact, there are public computer codes. You can download one yourself and run it on your computer to do these calculations, which relate the amount of matter in the universe to the amount of the elements we make. And in general, if you increase the density of matter, you make more helium and less deuterium, because deuterium is just a way station on the production of helium. So if you increase the density, the nuclear reactions go faster, they go toward completion, and everything wants to end up in helium, and you make less deuterium. And these calculations were first done in the 1960s by Jim Peebles, who won the Nobel Prize a couple years ago, and by Wagner, Fowler, and Hoyle. The basic framework has not changed all that much. We've simply improved the calculations, refined them, made them more exact. But what they tell us is that ordinary matter only makes up about 5% of what you need to make the universe recollapse. So before we learned about dark matter and dark energy, the assumption was that the universe would expand forever because it had way less matter than it needed to recollapse in the future. But in fact, there's more. And this more was first discovered by a fellow named Fritz Zwicky in the 1930s. So Zwicky, who was apparently quite a character, was looking at galaxy clusters. And here's some pretty pictures of galaxy clusters. So galaxies, as you know, are clusters of stars. They're hundreds of thousands of light years across, and they contain billions of stars. What's amazing is that galaxies themselves can be found in clusters. And so these are two famous clusters. This is the Fornax cluster, the Hercules cluster. There are a lot of these, and these things are almost unimaginably big. So, you imagine a galaxy, which is already enormous, and the galaxies themselves form these little clusters. I shouldn't say little. These are tens to hundreds of light years across, and they contain hundreds of galaxies. And what Zwicky was looking at was the motion of the galaxies. So once again, you can measure the motion of the galaxies using the Doppler effect, and he was comparing the motion of the galaxies to the gravity produced by the galaxies themselves. So you can look at these galaxies, estimate their mass, and figure out what's the mass of the galaxies and what's the kinetic energy. And what he discovered is that these clusters really shouldn't exist, in the sense that these galaxies are moving way too fast to be bound gravitationally just from the matter in the galaxies. And so he postulated that there was some kind of dark matter between the galaxies that was holding them together in these clusters. Now, sometimes in physics and in astronomy, it's dangerous to get too far ahead of our knowledge. And that, unfortunately, is what happened with Zwicky, because he essentially discovered dark matter in the 1930s, and people ignored this for decades. There was no other evidence for dark matter, and there was no reason to believe that there was really something exotic and weird there. So people knew, that there was something holding these clusters together, but the idea that there was some kind of exotic matter simply didn't enter into most people's minds. And so dark matter basically lay unexplored for about 50 years. And it was resurrected by Vera Rubin, who was a cosmologist working in the 1970s, and she was looking at the rotation of galaxies. And so, again, you can make these similar measurements. You can look at how fast objects are rotating around galaxies, and also look at the amount of matter in the galaxy and see if those two things make sense. And far outside the luminous part of the galaxy, that is way outside where all the stars and gas are, you're pretty much outside the galaxy itself. And so you can use Newton's law to figure out the speed at which things should move. So you can write down the formula for centripetal force, mv squared over r. You can write down the formula for the gravitational force, where m is the total mass of the galaxy, and you can cancel out little m, and you can solve for the velocity as a function of distance. And what you find is that the velocity should scale as 1 over the square root of the distance. And this is the same law that operates in the solar system. If you look at the distance of planets from the sun and their velocities scale like 1 over the square root of their distance. You can do this for Neptune and for Saturn, for Jupiter. And instead, what Vera Rubin found was that at large distances from the center of the galaxies, the velocity becomes a constant. It doesn't decay away, it flattens out. And she coined the term flat rotation curves, which means simply that as you go farther and farther away from the galaxy, the velocity, instead of going down, stays constant. And that tells you that there has to be some extra mass there, because this velocity is way too high. It shouldn't be this high. It should be decaying away. Instead, it's too high, and these objects ought to fly away unless there was some other source of gravity. And so what Vera Rubin and others postulated is that there was dark matter inside of galaxies. So there's extra dark matter And in fact, every galaxy we think is embedded in a spherical halo of dark matter. So here's the galaxy. It's a flat disk. This is just an artist's conception of our galaxy. And the halo extends way outside the galaxy, the halo of dark matter, and it's a sphere for various technical reasons. It doesn't collapse down into a disk because it can't give off radiation and lose radiation. Okay. So if you calculate how much dark matter there is in the universe by looking especially in clusters of galaxies, what you find is that it far exceeds the density of ordinary matter. So once physicists, cosmologists started looking at dark matter and doing these calculations, they realized that ordinary matter gives you about 5% of what you need the universe to recollapse, and dark matter was about 25%. So our form of matter isn't even the dominant form of matter in the universe. The dominant form of matter is dark matter. And then the obvious question is, what is the dark matter? Well, there are many theories of what it can be. Most likely, it's some sort of elementary particle, which is massive, which is stable or at least very long-lived because it's still around today, but it interacts only very weakly with ordinary matter, because if it interacted very strongly, we would see it. It would give off light or it would collide with particles in our detectors. So it's been called weakly interacting massive particles. And this is another way of saying we don't actually know what it's made out of. So the hunt for theories of dark matter is still very active, and people have come up with many different ideas about what this could be, and it's still unclear. So we're still very much in the hunt for what this is. And other theories have been proposed. For example, when the gravitational radiation from black holes was discovered, this resurrected the idea that maybe there were small black holes making up the dark matter in the universe. Now, that theory has a lot of problems, and I don't think it's very credible, but people have come to explore that more carefully. Some people have argued that we can modify our theory of gravity, our theory of relativity. That's very difficult to do, and I don't think those are very credible theories. But there's even more. So in 1998, two groups of scientists were trying to use distant supernovae to measure the expansion of the universe at early times. Now, what were they actually doing here? Well, what they wanted to do was to map out the expansion of the universe when it was much younger than it is today. So a telescope is sort of a time machine. And if you're looking up at the night sky and you're looking at stars that are hundreds of light years away, you're not seeing the sky as it exists today. You're seeing the sky as it existed. You're seeing these stars as they existed 100 years ago. Now, if you look at distant nearby galaxies, where we can map out the expansion of the universe and show that it satisfies Hubble's law, they're tens of millions of light years away. So you're looking back in the universe when it was, say, 10 million years old. But that's still a tiny fraction of the age of the universe. The universe is about 14 billion years old. And so what these scientists wanted to do was they wanted to trace the expansion of the universe back to when it was a significant fraction of its age. And why were they trying to do this? Well, these are different pictures of how the universe might expand. This is a universe that expands and recollapses. It's a high-density universe. This blue curve is a low-density universe. It expands forever. And this green curve is just balanced between expansion and contraction. So I should say this is the age of the universe, and this is the size of the universe. And so this is the present day. When you measure the Hubble parameter today, what you're really measuring is the slope of this line. So it doesn't tell you anything about the future fate of the universe. All it tells you is how fast the universe is expanding today. And all of these curves can lie on this line. You can't see into the future of the universe, so we can't see directly what the universe is going to do. But these different future fates of the universe correspond to different past evolution as well. And so the idea was to go out to when the universe was a significant fraction of its age younger and measure the expansion out here and figure out which of these curves we're sitting on. Now, to do that, you need a standard candle that will operate very, very far away. So Cepheid variables won't do that for you. And in fact, the only objects that are bright enough to see billions of light years away are supernovae. And in fact, what are called type 1a supernovae. They're supernovae that occur when a small star is accreting mass from a larger star, and then the whole thing explodes. And what these two groups, Saul Perlmutter, who's now in Berkeley, and the Harvard group did, was they looked at the typical curves of supernovae, that is the typical brightness of supernovae, how fast they get bright, how bright they get, and how fast they get dim. And they were able to correlate these histories with the absolute brightness of the supernova. That is to say, supernova that took longer to get bright and longer to get dim had a different intrinsic brightness than supernova that got bright fast and got dim fast. So they basically redid what Hubble did, but instead of using Cepheid variables, they actually used supernovae. And they were able to use this to measure the intrinsic brightness of supernovae and then correlate that brightness with how bright they appeared. And then they could measure the distance of very, very distant galaxies and measure their expansion rate. And then they were able to measure not just the slope of this line here, the Hubble parameter here, but the slope of this line at earlier times. And they made an extraordinary discovery, and in fact, a discovery that I would say nobody was expecting. Now, after the fact, a number of theorists came forward and said, oh, I predicted that. But in fact, what they showed is that these three fates for the universe, eventual collapse or infinite expansion, or balancing in between these two, the universe didn't lie on any of these three curves. In fact, it was on this red curve. And the red curve is really bizarre because it slows down, but then it accelerates at late times. So it would be as though you threw an apple into the air, and instead of slowing down as it flew out of the Earth's atmosphere, it slowed down initially, but then it accelerated. So what these groups had shown is that on very, very large scales, the action of gravity is not attractive, it's repulsive. That is, gravity is not attracting very distant objects away from us, it's repelling them. And this is impossible in Newtonian gravity. If you study, Newton's law of gravity always attracts. But in Einstein's theory of relativity, there are some exotic forms of matter that have repulsive gravity. And so we need, in order to explain this evolution, we need something called dark energy. Now, dark energy has very weird properties. For one thing, it doesn't get more dilute as the universe expands. So with dark matter and ordinary matter, as the universe expands, atoms and molecules move farther and farther apart and their density goes down. As the universe expands, the density of dark energy stays the same, which is very kind of weird. We believe it has negative pressure, and that's because that's what you need in Einstein's theory of gravity to produce repulsive gravity. It doesn't cluster at all. It's smoothly spread out throughout the universe, and it probably only feels the force of gravity. It doesn't interact in any other way, and it, in fact, gives you repulsive gravity. So when we then go back and ask what is the universe made of, this dark energy is not only the most exotic component in the universe, it's also the most abundant. It seems to make up about 70% of the energy density in the universe, with the remainder being in the form of dark matter and then finally ordinary matter. Now, these measurements are compelling, but they're certainly not conclusive. And I think people really didn't believe in this picture of the universe until it was confirmed with a completely different set of observations. And these observations are observations of what's called the cosmic microwave background. This confirmation came in the year 2003 from the WMAP satellite, which was mapping out the microwave radiation in the universe. Now, what is that all about? Well, if you looked at the sky in the early universe, if you could see the sky in microwaves instead of visible light, and if you could and you could get up above the Earth's atmosphere, because the Earth's atmosphere blocks out a lot of these microwaves, and if you remove the microwaves that we see from the galaxy itself, this is what the universe would look like. And this is radiation that's left over from the Big Bang. So the universe started out in a very hot, dense state, and as it has expanded, this radiation has cooled, and the bulk of the radiation that's left over from the early universe is in the form of microwaves. And the microwaves, when they were first detected in 1965, were thought to be completely smoothly distributed in space, but it was soon realized that they ought to have tiny little fluctuations in them. They should have hot spots and cold spots, and that's what you're seeing in this picture. There are bright spots where the temperature, the intensity is higher of the microwaves, and cold spots where the intensity is lower. And this is a relic of the formation of galaxies in the early universe. We think the universe started off with tiny ripples in the density, and with time, under the force of gravity, those ripples grew with time and gave us density enhancements, which went on to become galaxies. And the process of forming those galaxies imprints itself on the radiation. So the radiation gets partially dragged along, and it sees the hot spot, this formation process. And the important point is that the actual pattern of radiation that you see is very sensitive to what the universe is made of. A universe that was 100% ordinary matter would give you a very different kind of pattern than one that has dark matter in it. And one that has dark energy in it has a very different pattern from one without dark energy. And so you can use these microwave measurements, which have gone on after WMAP. There was an even more sensitive instrument called Planck. And so we've been able to map out these fluctuations very, very sensitively, and then extrapolate back to say, how much dark matter do we need and how much dark energy do we need to give us this kind of pattern? And what we find is that it's exactly what we've predicted from other measurements. That is, the universe should be mostly dark energy, about a quarter dark matter, and only a tiny fraction in ordinary matter. So how do we look for these things? How do we look for dark matter? Well, the hunt for dark matter is very, very active. And there's sort of three different ways we can try to find dark matter. We can look for it directly in particle accelerators. We can look for it in underground detectors. And we can look for kind of astrophysical signatures of it. So the first of these is to try to make dark matter in a particle accelerator. If you could actually make a particle in a particle accelerator, that would be the best result of all, because you could study the dark matter particle directly. You could figure out its properties, its mass, all of its other properties, and it would be like having a butterfly in your butterfly collection. You could look at it very, very precisely. And so one of the hopes when the Large Hadron Collider turned on is that it would detect dark matter. Now, a lot of people didn't believe that it would. It has not seen evidence for dark matter. What it has done is push up the lower limit on dark matter, because there's a limit as to how massive a particle you can make in the Large Hadron Collider, and we haven't seen it there. So this so far has not turned up a good dark matter evidence for dark matter. Another way to find dark matter is what are called direct searches. And so in these direct searches, you go down in a mine shaft or some other shielded place where cosmic rays can't penetrate, and you get a big vat and you fill it up with stuff. And then you wait for a dark matter particle to come through the Earth and hit one of your nuclei, and you would detect it. So if you're going to do one of these experiments, you need to be able to go down into a deep mine shaft, and you need to be very, very, very patient, because you're not going to see vast signals from these experiments. Lately, the object of the stuff of choice is liquid xenon. So xenon didn't have very many applications in the world, but now it does. It's the element of choice to put in these dark matter experiments. It's an inert gas. It has a nice nuclear properties, and the nucleus is massive enough to recoil nicely from what we hope is the right dark matter mass. And so far, these experiments have also not detected dark matter. But what they've been able to do is put an upper limit on how much it interacts with ordinary matter. So these experiments are getting bigger and bigger and bigger, and as they get bigger, you can see the limits go further and further down. And that's the advantage of these experiments. Unlike the Large Hadron Collider, where you built a collider and now you're kind of stuck with it, you can't make it any bigger easily. With these experiments, you can just make bigger and bigger and bigger vats of liquid xenon, and that makes your experiment more and more and more sensitive. And that's what people are doing now. And again, we haven't seen anything, but the hope is that this is where dark matter would turn up. And my own personal view is that these are, I think, the most likely to be successful. If we're going to see dark matter in the next decade, I think they're going to turn up in these experiments before they turn up anywhere else. But a third approach is to look for signatures of dark matter out in the astronomical universe. So, for example, you could imagine that you have dark matter particles and anti-dark matter particles, and they can annihilate, and they might produce gamma rays because they're the right mass to make gamma rays. And so, for example, the Fermi Gamma Ray Space Telescope looks for these kinds of backgrounds. Now, the problem with these experiments is not that they see nothing. So, at the Large Hadron Collider, we've seen no evidence for dark matter. At in these deep underground experiments, we've seen no evidence for dark matter. The problem with astrophysical signatures is that you see all kinds of backgrounds. And so there are lots of weird gamma ray, X-ray backgrounds out there that aren't entirely explained. And so every time a new background is discovered, theorists jump on it and say, oh, this has got to be dark matter. So right now, there actually are several different signals that have not been entirely explained that people have interpreted as possibly dark matter. The problem with this is that astrophysics is a really messy subject, unlike cosmology. Cosmology is very clean. Astrophysics is very messy. And there are many different ways of making radiation. We've learned this since the dawn of astronomy. You can see all kinds of different things. And so it's most likely that any sort of weird, unexplained background you see could be produced in some other strange, exotic, neutron stars or pulsars or something are accelerating particles and generating radiation. So with these kinds of detection experiments, the difficulty is trying to show that something really is due to dark matter and not to something else. Now, how do we look for dark energy? Well, dark energy is much more difficult to look for because we think that it doesn't interact directly with ordinary matter, and it's not clustered. And so really with dark energy, what is going on is people are simply trying to do the standard experiments better and better and better, because that gives us a handle on how the dark energy evolves, and that gives us a clue as to what it's made of. So we don't have a direct way of detecting it. All we can do is repeat these experiments and try to map out the expansion of the universe better and better. So the ground-based surveys have continued and have gotten more and more and more data. There's a space telescope that's going to launch. It was originally named W-FIRST. It was renamed after a woman named Nancy Grace Roman. It's now the Roman Space Telescope. And it's a space observatory that will allow us to measure more accurately the expansion of the universe. It has other purposes as well. It's an infrared telescope. It can help look for planets and that sort of thing, but it's a multi-purpose space telescope. It hasn't been launched yet, but it's on the book. So we'll see if it gets up there. But these two things are likely to give us a much better measurement of how dark energy is behaving. So where do we stand now? Well, it's an interesting time to be working in cosmology because it's much more clear than when I first got started in the field. When I first began in the 1980s, there was very little data and a lot of speculation, and you could come up with almost any theory you want and no one could prove you wrong. Now we have a much more precise idea of what the universe is made of. And in fact, many cosmologists talk about the era of precision cosmology. That is, we know a lot of the numbers that govern the expansion of the universe. And yet we don't have any idea what the universe is made of because we don't really know what dark matter and dark energy are. And so that's a very exciting time to be involved in cosmology. Okay, let me stop there and I can take questions. Let me exit out of this.
Yeah, thank you, sir.
Okay, should I click on stop screen or not?
No, 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 no. It's
No.
okay.
Okay. Okay.
Yeah. So we have got few questions. So if you allow, we can start discussion
Sure.
session. So the first question I can add. So is the universe made of string, a quantum form, or a spin form, or Planck length size scale?
Okay, so that's a very good question. And what you're referring to is some theories of quantum gravity. So, ultimately we know that our theory of gravity or our theory of quantum mechanics, one of them has to be modified, possibly both of them. And the reason is that they give contradictory predictions. For example, near black holes, you can get contradictory predictions from quantum mechanics and from relativity. And we've never really needed to unify those to deal with most of the phenomena we see on Earth and the solar system. But we don't really have a quantum theory of gravity. And so people have proposed various theories like string theory and loop quantum gravity. And ultimately, those are the theories you need to understand how the universe behaves in the very, 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 very early universe, or how it behaves on the very smallest scales. But in fact, I would argue at this point, we don't really have a compelling theory. So there's a lot of theories out there, but none of them are experimentally verified. And so the answer to the question is we don't know the answer to the question yet.
Sir, thank you. We have another question in inbox. So, what are the variable stars?
What are the variables? So variable stars pulsate. And most, like our own sun, is not a variable star. It would be very bad if it was a variable star, because it would get very hot on Earth and then it would get very cold. But some stars pulsate, and as they pulsate, they expand and get dimmer, and then the energy is not enough to keep them out there, so they contract and get brighter again. And there are various types of variable stars. It's a whole other area of astronomy that people study in great detail.
Thank you, sir. We have another question in inbox. What are the effect of dark matter and dark energy on expanding universe?
Well, the dark matter dominates the expansion of the universe early on. So when the universe was younger than it is today, it was the thing that made the universe, gave us the rule for how the universe is expanding. The dark energy is now the dominant component, and what it's doing is it's actually driving the universe to accelerate. So, when something expands under the action of gravity, it always slows down. If you shoot an object off the Earth's surface, even if it escapes from the Earth, it slows down as it moves away from the Earth, because it's rising out of a potential well. But the effect of the dark energy is to act as repulsive gravity, and it's making the expansion of the universe accelerate today. It's going faster in the future rather than slower.
Thank you, sir. We have a question from Dipan Bhattacharya sir. He's asking that what is your best guess for the source of dark matter?
Well, I'm still guessing that it's a heavy particle. Now, partly, you should always ask people when they make these guesses what research they've done in the past. I, of course, have done research in this field, and so I feel like it's my baby. It's something I've done. But I think we really don't know. And I think if you'd asked cosmologists 10 years ago, almost all of them would have said it's certainly some heavy particle. But the fact that we haven't discovered it yet in these various searches is making it look less and less likely. The problem is we don't have that many good alternatives. So I'm guessing a heavy particle. Other people will tell you it's something else.
Okay, sir, thank you. We have another question. So what is the role of neutrinos in shaping our universe?
Well, actually, they play a very important role throughout the expansion of the universe. So in the early universe, they affect the production of elements. And in fact, that's how we first predicted how many neutrinos there ought to be in the 1970s based on these predictions for element production. Now, they're not a dominant component, they're subdominant, but they have a very small mass. And so they shape, to some extent, the way that galaxies cluster in the early universe. So they always have to be taken into account. They're an important component of the expansion of the universe. And so when you do calculations in cosmology, you always have to include the contribution from the neutrinos. They definitely, contribute to all of these effects that we've talked about.
Yeah, thank you, sir. We have another question. So presently, when we say gravity in astrophysics, is it Newtonian gravity or gravity described by Einstein?
Well, it's both. So the best way to think about this is that the theory of Einstein's gravity is the true theory. It is the correct theory of gravity as far as we know. We have seen no exceptions to it. But if you want to calculate most things, it actually is very, very difficult to calculate things in Einstein's theory. But if you look at objects that are moving slowly and the gravitational fields are weak, Newtonian gravity is really the limiting case of Einstein's gravity. So it's what Einstein's gravity looks like for most of the universe that we deal with. So in most practical applications of gravity, when you calculate the orbits of, when you calculate a rocket going to the moon, you don't have to correct for relativity. If you want to do very, very precise calculations, you need Einstein's gravity. So the term gravity is actually ambiguous. In cosmology, it always refers to Einstein's gravity because you need Einstein's gravity to give you the correct law. But for many applications in the structure of stars and that sort of thing, you can use Newtonian gravity. And as I said, the way to think about it is just a special case of Einstein's gravity.
Yeah, thank you, sir. We have another question. So it is said the universe is continuously expanding. What causes it to expand, and will the universe expand further?
So the expansion of the universe is built into the initial conditions, and we don't know where those initial conditions came from. Sorry, are you still there? Your picture disappeared. Are you back? Okay. But I forgot to say, I should have said this because I kind of left you hanging when I talked about whether it would expand forever or recontract. Once you enter a phase where the universe is accelerating from dark energy, then it does expand forever. And so if that theory is correct, and again, I should always say if the theory is correct because we can always be proved wrong by future observations. But if the theory of dark energy is correct, it will expand forever. And not only that, but it'll expand at a faster and faster rate.
Thank you, sir. We have another question. So how many rogue planets are there? And can rogue planets support life?
Well, we don't know how many there are. This is not my field, but I can give you an amateur's answer. We don't really know how many there are. And, the simple answer to the question is it would be very difficult for them to support life because life needs energy of some sort. Now, if you had, on the Earth, if the sun went out, we would all die. But these animals that live in hydrothermal vents at the bottom of the ocean would do just fine. Well, they would do just fine for a while because their energy source is the geothermal energy of the Earth itself. It's a very interesting question, and I think you could come up with some kind of wild ideas about how life might survive on a rogue planet, but not life as we know it anyway.
Thank you, sir. We have another question. So universe is now expanding, but if it collapses, when the universe will collapse, and is it any approximate time?
Well, we don't think it's going to recollapse. Now, there are people who've come up with ideas that try to incorporate dark energy and have the dark energy change its behavior in the future, and then the universe would recollapse. It can't recollapse in any less time than it took to expand, I think. So I would give us at least another 15, 14 billion years. We're safe.
Okay, sir. Thank you. So this may be the last question. So how large is the entire universe, and do we need to know the unobservable universe to know what the entire universe is made of, or the observable universe is enough?
So that's a good question. So the observable universe, remember that the universe is about 14 billion years old. So that you can only see out to a distance of 14 billion light years. Anything beyond that is just, invisible to us. We think that the universe is probably infinite, but there's no way to know. And so we just extrapolate from what we see to the universe that we don't see. But there's really no way fundamentally to know. And that gets down to questions about the fundamental nature of science. If there are things that can never be observed, from a scientific point of view, you really can't say anything intelligent about them. So I won't say anything.
Yeah, thank you, sir. Thanks for your wonderful and exciting lecture and exciting discussion session. So I got another question. So before
Okay.
going to end, we can take that question. So how are gamma ray bursts detected, and what is the role of gamma ray burst in the history of the universe? Are gamma ray bursts difficult to study?
Well, that's a very interesting question. I'll give you the historical answer. So, in the United States, the military launched satellites to detect gamma rays from atomic bomb tests from the Russians and others. And so the idea would be to look down on the Earth, and if there was an atomic bomb that blew up, it would give off a burst of gamma rays, and you'd see it in your satellite. And what they discovered was that there were gamma rays that weren't coming from the Earth at all. Now, they didn't tell anybody about this for a while because it was all very secret and hush hush. But when they finally told people this, and suddenly people said, "Oh, there's gamma rays coming from other places in the universe." Now, they are well, I don't know. They're difficult to study only in the sense that you can't see them from the Earth's surface because the atmosphere blocks that radiation. So you have to look at them using satellites. And they're thought to be, after the LIGO discovery, at least some of them are due to neutron stars that are emerging. But they play a role in astrophysics, and some people want to use them as standard candles to map out the expansion of the universe, but that work hasn't gotten very far yet.
Okay, sir. Thanks again. So it is a very good opportunity for us, including we actually with the faculty member, for learn a lot of things actually about our universe. So thanks again. I would like to say thanks on behalf of the Department of Physics for giving us time.
Okay.
And it's our honor and privilege to host this in our International Physics Center.
Okay.
So bye for today, sir.
Okay. Bye-bye.
Bye. Have a nice day.
Thank you.